Today we're going to talk about what is maybe the most basic type of fraction, and that is a unit fraction. So those are fractions of the form 1 over m, where m is a natural number. So in other words, just reciprocals of natural numbers. And in fact, I think most historical developments of the rational numbers start with the unit fractions. I know that unit fractions are very important in Egyptian mathematics. There's a so-called Egyptian fraction decomposition for certain rational numbers. Maybe post in the comments if you'd like to see a video about that. I'm always down for a nice math history video. But that's not what we want to look at here. We want to look at a little bit of a broad question, and that is, given a natural number n, how many ways can we decompose the unit fraction 1 over n as the sum of two unit fractions? So in other words, 1 over a plus 1 over b, where those are both natural numbers. So in my mind, this is kind of in parallel to the theory of integer partitions. So if we didn't have reciprocals here, we would be asking how many ways can we write n as a plus b, where a and b are natural numbers. But that would be exactly the number of partitions of n with two parts. And so maybe this type of question would be like a partition theory type question for these unit fractions. So is this partition theory for unit fractions studied? Well, to be honest, I don't really know. I know quite a bit about integer partitions, but I've never heard about the study of partitions of unit fractions like this. But I think it could make an interesting project if there's not much known about it. Okay, so let's start with an example. And maybe the example we'll start with is fairly simple. It's 1 over 10. So let's try to decompose 1 over 10 as 1 over a plus 1 over b. That'll give us an idea for how to do this in general, although we will do an example in the middle. So what I'd like to do, even though we're working with fractions here, is to clear the denominators. So we can clear the denominators by multiplying both sides by 10 times a times b. So that'll give us a times b on the left-hand side, and then 10a plus 10b on the right-hand side. So multiplying this by 10ab, the b's will cancel and we'll be left with 10a, and likewise for this 1 over a term. And then from here, the general strategy is to complete the product. So what I'll do is move the 10a and the 10b over to the left-hand side, and then simultaneously add 100 to both sides of the equation. That's this completing the product strategy. So we'll have ab minus 10a minus 10b plus 100 equals 100. I guess it's important to notice here that 100 is equal to 10 squared. So the square of this number will be important in the general case. But now we've written this left-hand side so that we could factor it. Like I said, we're trying to complete the product. So let's factor it. Notice that it will factor as a minus 10 times b minus 10. So if we were to FOIL this out, we get exactly the left-hand side of the above equation. So that's good. And then we have this is equal to 100. And now we just want to think about all the different ways that we can factor 100 and split all of those different ways among a minus 10 and b minus 10. So maybe we could first have 1 times 100. So that's not maybe super interesting, but that is most definitely a way to factor 100. We could have 2 times 50. We could have 4 times 25. We could have 5 times 20. Next, we could have 10 times 10, and then we would go back down. But we're going to leave it like that because even though I didn't say it, we're going to assume that the order doesn't matter in this summation over here. So for example, if we had like 1/3 plus 1/2, we would consider that the same as 1/2 plus 1/3. Okay, so now what we'll do is think about this column right here as being what is assigned to a minus b, and this second column right here is what's being assigned to b minus 10. Okay, so let's see how many possibilities that will give us, and then we'll actually write down some of the possibilities. So we get a possibility from here. So 1, 2, 3, 4, 5 total possibilities. Now we could write those down if we wanted to. So if we have A minus 10 equals 1 and B minus 10 equals 100, so that means we have A equals 11 and B is equal to 110. But now that means that we have the equation 1 over 10 equals 1 over 11 plus 1 over 110. So that's one such decomposition of the unit fraction 1 over 10. And then maybe we'll pick one kind of in the middle. So let's pick this 4 times 25. So that would be A minus 10 is equal to 4. And then B minus 10 equals 25. So that gives us A equals 14 and then B equals 35. So that gives us the following decomposition. 1 over 10 equals 1 over 14 plus 1 over 35. So that's another such decomposition. And then we obviously have the one where they're both equal to 10. And I won't do the calculation for that. It's pretty simple. And that will give us 1 over 10 equals 1 over 20 plus 1 over 20. And that's allowed as well. So those are 3 of the 5 possibilities. You can write down the other possibilities if you'd like. So let's maybe look at one more example before we do this in general. For our next example, we will decompose 1 over 2022 as 1 over A plus 1 over B. So maybe we could call this something like unit fraction partitions of a unit fraction if you wanted to put this in line with integer partitions. Okay, so how should we start here? Well, I think it's going to be pretty similar to what we did before. So let's clear the denominators. That'll mean we multiply by 2020 times A times B. That will give us A times B equals 2022A plus 2022B. And then we'll move things around and then complete the product. That will leave us with A times B minus 2022A minus 2022B. And then to complete the product, we'll add 2022 squared, but then we have that on the other side of the equation as well. So 2022 squared. And then I'd like to quickly notice that 2022 has the following prime factorization, which will give us the similar prime factorization for 2022, and that is 2 squared times 3 squared times 337 squared. So 2 times 3 times 337 is the factorization of 2022. So when you square it, you have to square all of the prime factors like that. Okay, so now let's factor this left-hand side. That'll give us A minus 2022 times B minus 2022 equals, maybe we'll just like bring this equals right up here. Okay, and now we've got similar choices to as we had before. So we can factor this maybe like according to the primes, but maybe there's a smarter way to do it for counting purposes. And I think there is. And that is, notice that A minus 2022 must be of the form 2 to the, let's maybe say R1 times 3 to the R2 times 337 to the R3. Then after we've made the choice for A, the choice for B is fixed. So we only really need to think about how to choose A. Then how many choices do we have for R1, R2, and R3? Well, they each have 3 choices. So R1, R2, and R3 can come from the set 0, 1, or 2. That's because our highest power for each of those primes is 2. So we were lucky that they all went up to 2. They could have been something else. Okay, so what does that mean? So we've got 3 choices for our power of 2, 3 choices for our power of 3, 3 choices for our power of 337. So all told, using the multiplicative property, there will be 3 times 3 times 3. In other words, 81 choices for A minus 2022, and thus 81 choices for A after adding the 2022 over. But now let's notice that that overcounts almost all of the possibilities, because we have that kind of symmetry between 1 over A and 1 over B. So we need to take that into account. The only possibility that it does not overcount is the possibility where A is equal to B. So that's going to be on its own. So we have real possibilities over here. So maybe we'll put unique to say the unique possibilities in the end. So we'll have this number 1, which is the case when A is equal to B, plus 81 minus 1. So that 81 minus 1 will be all of the possibilities when A is not equal to B. So let's write that here. So this would be all of the cases when A is not equal to B. But then by the symmetry between A and B, we have to divide that by 2. So now putting this together, we've got 81 minus 1, which is 80, divided by 2 is 40, plus 1 is 41. So in the end, there are 41 possible ways to choose A and B to do this decomposition. So let's maybe work through a couple, maybe just one possibility real quick. And notice that, for instance, if we choose A minus 2022 to be equal to 2 times 9 times 337. So that would be all of the 3's, but one of the 2's and one of the 337's. That means we'll have B minus 2022 is equal to 2 times 337. And that gives us the decomposition of 1 over 2022 is equal to 1 over 8088 plus 1 over 2696. Great. So that would be one of these 41 possible ways of decomposing our 1 over 2022. Okay, so now let's revisit this question for an arbitrary n. So let's see a little bit of what's going on in general here. So let's take our number n and write it with its prime decomposition. So we'll write it as P1 to the R1 all the way up to PK to the RK. And this is where all of the PI are distinct primes, and then maybe the RI are all bigger than or equal to 1. Okay, so we've got something like that going on. Now we'll take 1 over n and we seek to write that as 1 over a plus 1 over b, but that means we have a over b is equal to na plus nb. So now we can move some things around just like we have done before, and we'll get a times b minus na minus nb plus n squared is equal to n squared, just as before. But now let's rewrite the n squared on this side of the equation as p1 to the 2r1 all the way up to pk to the 2rk. Great. And now we've completed our product over here, so let's take advantage of that. So this is a minus n times b minus n. So let's see what we've got. We've got this a minus n times b minus n is equal to this following product of primes. So that means that we have a minus n must be of the form p1 to the, let's maybe call it s1, all the way up to pk to the sk. And then what are the possible choices for these s's? We'll notice that each si is between 0 and 2ri. Could be 0 if it does not include one of those prime factors. It could include all of the possible prime factors. So how many possible choices are there here? Well, there are 2ri plus 1 possible choices. So that means without worrying about overcounting, there are a product of numbers like this, number of choices for a minus n. So let's write that down. So 2r1 plus 1 times 2r2 plus 1 all the way up to 2rk plus 1 total choices for a minus n. And that's without worrying about overcounting at all. So now let's look for our unique choices just as we finished off that last example. So for our unique choices, we have the number 1. So there's one unique choice based off the choice when A is equal to B. And then after that, we'll have n minus 1, where n is equal to this number right here, this big product. And this n minus 1 is based off the case when A is not equal to B. But then by the symmetry of A and B in our decomposition, we have to divide that by 2. And then maybe we could put this together to simplify it. Notice we'll put it together to get n plus 1 over 2, but we might as well write n1 as this big product. So 2r1 plus 1 multiplied up to 2rk plus 1, and then plus 1 on the outside all over 2. So that would be our total number of ways of decomposing our number n into a sum of 2 unit fractions. And that's a good place to stop.